Hi, this is the first lecture for Z-transform. So what's Z-transform? Z-transform for discrete time function is a convenient and powerful tool for the solution of difference equation, analysis of linear time invariant system. In Z-transformation, it converts the discrete convolution into a product operation. So it makes life easy dealing with discrete system. Well, what is the definition of Z-transform? How can we transform discrete signal or sequence into Z-transform? What's look like? So the objective is we have a sequence and we need to transform it to Z transformation, X capital of Z. And it's defined as summation. So X of Z, the Z transform of any discrete sequence is equal to summation from n minus infinity to infinity, and the sequence times Z power minus n. And Z in general is a complex variable, has a real and imaginary. So how can we perform this operation? Before we do that, just let's evaluate this summation. Start by substituting from n minus infinity to infinity in this expression. So you can say that X of Z is equal to, I'm not going to start from minus infinity, I'll just make dots till I arrive to, let's say, X when n minus 2. So when you have X of n minus 2, you substitute here n minus 2, negative and negative will be positive, so it will be Z squared. X minus 1, Z power 1, plus X 0, Z power 0 is equal 1, plus X 1. Now I'm going to n positive. You put n equal 1, you put n equal 1, so it will be Z power minus 1, or negative 1, plus X2, Z power negative 2, and so on. So what you observe here, that's the value of the sequence at n in negative 2 multiplied by Z squared. And that's the value of the sequence at n equal negative 1 multiplied by Z. What do you observe? You observe that the index of any element in the sequence, its sign opposite to the sign of the power of Z. So this one is negative 2, the power is 2, Z squared. When you go for 2, X of 2 here, you find that the power of Z is equal negative 2. So the opposite sign. So this is very observation. What do you observe from here? You observe that the sequence, and instead of having like samples at each instant, it's going to be expressed as a series, as a sum, as you see here. Well, let's just take a very simple example to see how it looks like. Let's say they have a sequence defined over n, and that's the vertical axis, and I'm going to sketch or plot this function. So it's 0 at the negative n, and at 0 still 0, and at 1 is equal 1, at 2 is equal 2, at 3 is equal 3, at 4 is equal 4, 1, it's equal 3, and after that it's going to be 0 again. So that's a sequence, you see. And at each instant, it's defined the value of the sequence. I want to find the transform of this one. So I'm going to use this definition, this summation, this series. So how do you write that? Well, actually it starts from 1. So I will start writing from this term because everything is 0 behind that. So I'll say x of z is equal to x1 multiplied, we agree about that to be the negative of the number, plus x2 z power negative 2, x3 z power negative 3, plus x4 z negative 4. I'm not going to continue because it's going to be 0 after that. So that's, I'll stop here. Now I will start substitute by the values of x1, x2, x3, x4 in this sequence. x1 is equal 1, so I have only z minus 1. x2 is equal to 2, so I have 2, z minus 2, and the last two values, they are equal to 3, z minus 3 plus 3 z minus 4. So that's the transform of the sequence that was given. Okay, so it's an easy thing. Of course, you want to find closed form. How can you find closed form of the Z transform? Well, there are, as we did before, some formula in geometric series that they are helpful. And let me just remind you by some of them. Excuse me. For geometric series, we know that the sum of a to the power of n, when n from 0 to infinity, that will be equal like 1 plus a squared plus a cubed, and then just will go the n. If the magnitude of a less than 1, small number, so you can approximate this one, 1 over 1 minus a. That's 1. There are many. I put them in the handout, and just let me give you another one. If you have the summation from n equals 0 not to infinity, some number n minus 1 for geometric 1, that will be equal to 1 minus a power n divided by 1 minus a. For example, if you have n equal to 10, so the summation for n equals 0 up to 9, a power n will be equal 1 minus a power 10 over 1 minus a. That's an example. So, they are so important for evaluating a closed form of x, z transform. Well, let's now find or get another function like unit step. If we want to find the unit step, example 2, let's say that the sequence that we have, unit step sequence, and we know how to sketch this one. If this is 0 and this is minus 1, minus 2, 1, 2, 3, and so on, start from 0 to be equal 1. If we say this is 1, so it'll be 1 all the way. All right. So now I want to find the transform of unit step. Well, according to the definition, it's xn z power minus n, n minus infinity to infinity. That's the definition. So, but since the unit steps start from 0, so I will change this limit from n equals 0 up to infinity. And the value of xn, as you see, it's equal, since I'm working with unit step, is equal 1. So I'm going to change this to 1. So I can just write this one in this way, in a simple way, from n equals 0 up to infinity, and you have z power minus 1 all power n. Why I'm doing that? Remember, that's geometric series from 0 to infinity. A power n can be represented as 1 over 1 minus a. So I'm trying to make it like that. So this is like my a. So you can approximate as 1 over 1 minus a, and my a is equal like that. So that's, I mean, the z transformation for the unit step. But there is a condition. We said in geometric series that this approximation is valid only when the magnitude of a is less than 1. The same thing has to be done here. We have to say that z minus 1 should be less than 1. Okay? So it means 1 over z less than 1. So if you flip it, you'll find z greater than 1. So this one is valid when the magnitude of z greater than 1. We call this ROC. What does it mean? Region of conversion. It means this expression is not valid except only if this condition is valid, except if z magnitude lies in the region of the conversion. This is the region of the conversion. All right. I want to say something also, just to make it easy when you solve problems. That's what we found. That's the z transform of unit step is equal 1 over 1 minus z minus 1. Sometimes some people, they don't like deal with negative power. So what you're supposed to do, you can multiply it in the top by z and the bottom by z. If you multiply z by 1, z equals z. Z times b equal 1 and the top z. So these two forms are valid. 1 over 1 minus z minus 1 or z over z minus 1. Whatever you like to do. All right. Let me take another example. So you'll be familiar how you find z transform. Okay. The second example is x of n is equal to a to the power of n u n. And a is a constant. For example, I mean, you may be asked, find this one. Remember, when you add to any function un, it means that will be valid only when n greater than or equal 0 and 0 otherwise. So anytime you find un attached to a function, it means defining the range of n. That's all. So now I want to find xz of this one. I'll just rewrite the formula. The summation, it's the sum of n minus infinity to infinity x of n z power minus n. And also, I want to say something. I mean, when you read some textbook, maybe instead of writing n, write k, small k. That doesn't matter. Anyway, since it's multiplied by un unit step, it means it's going to start from n equals 0. So again, we're going to modify this one from n equals 0 up to infinity. And xn is equal an in this region. So you replace this one, a power n. And we are going to adapt this to make it look like a geometric series. So how we do that? You just want to make something power n. All right. So you have a inside, and you have z minus 1. That's it. So how you approximate this one? See, it's almost 1 over 1 minus all this inside the bracket. A z minus 1. That's it. So this is z transform of a power n. And again, if you don't like to have z power minus 1, we want to have a positive power, multiply by z in the top, and the z in the bottom. And that's, I mean, a very useful formula. So that's how you find z transform of a power n. All right. I think, I mean, that's, I mean, good 3 examples, and there are more examples in the handout. I hope that you understood.